Good morning, children. This is 12th Physics, Chapter 4, Magnetic Effects of Current. Let's start with that. Right? Now, magnetic effect. It was the scientist Oersted. Through his experiments, he related electricity and magnetism. Let's see what experiment did he perform. He had an experimental setup which consisted of battery, switch, and magnetic needle which was pivoted on a stand, means which is kept on a stand. Now, the direction of current is along the south-north direction. As you can see, the direction of current is along the south-north direction because we know that the magnetic needle gets aligned towards the north-south direction, right? Now, when the switch was on and as the current flow through the wire, the magnetic needle got deflected towards the west. The North Pole got deflected towards the west. Right? So after deflection, you can see the dotted blue color shows you the deflected position when the current flows through the circuit. Right? Then Mr. Oersted, he reversed the direction of the current. See what he has done. The negative of the battery is over here and the positive is on the other side. Initially, it was reversed. So now he has reversed the terminals of the battery. So on reversing the terminals of the battery, the direction of the current will be reversed. So now the current flows from north to south. And when the current flow from north to south, the magnetic needle which was kept near it got deflected in the opposite direction. That is, initially it had got deflected towards the west, the North Pole got deflected towards the west, but on reversing the direction, the North Pole of the magnetic needle, it got deflected in the opposite direction. That is, it got deflected towards the east, right? So on changing the direction of the current, the magnetic needle deflection also changed. Here children, the magnetic needle is getting deflected and we know that the magnetic needle, it gets deflected to show the presence of magnetic field. So here Oersted related that when a current carrying conductor is present, the current carrying conductor produces magnetic field also. Current, it creates magnetic field in the space around it. So when current was flowing through this wire, magnetic field was created, and because of that magnetic field, the magnetic needle gets deflected. So it is with the help of this experiment that Oersted showed that electricity and magnetism, they are interrelated. Wherever there is current flowing, magnetic field has to be there. Right, children? So they both are interrelated with each other. Okay, then he did one more experiment, and then in this experiment, this is the wire through which the current is flowing, and around the wire at different position he placed the magnetic needle. So here we can see that the magnetic needle gets deflected in order to show the North Pole. So the magnetic needle got deflected and we got the circular direction. And it was seen that on reversing the direction of current in the wire, now initially the current was moving in the upward direction, and in the second case we are reversing the direction of the current. So as the direction of the current got reversed, the direction of deflection of the magnetic compass also got reversed, right? So here you can see that the magnetic needles, their direction is reversed. Then he did one more experiment in which what did he do is he had taken a straight wire, and in the wire he is passing the current in the upward direction. This wire he is passing through a cardboard. This is a bit of cardboard, right? And on the cardboard he is sprinkling some iron fillings, iron dust, right? And when the switch was on and the current flows through this wire in the upward direction, it was seen that the iron dust, it got arranged themselves in the form of circles, right? It was seen that the iron fillings got arranged themselves in the form of concentric circles, right? So, and on reversing the direction of the current, now if suppose the direction of the current becomes in the downward direction, again the iron fillings got arranged themselves in the concentric circles only, but this time the direction was reversed, right? Reversed from the previous one. If initially the direction was anti-clockwise, now the direction changed to clockwise. So this was your Oersted experiment, and he showed that the current depends upon the magnetic field. Sorry, the magnetic field direction, it depends upon the direction of the current. On reversing the direction of the current, the direction of magnetic field can be reversed, right? So here is a rule which helps us to predict the deflection of magnetic needle in Oersted's experiment. So this is also known as Ampere's swimming rule, or there is one more name for this, that is snow. With the help of this rule, we can find out the direction of deflection of needle, कि needle किस direction में deflect होगी, right? So let's read out the rule. The rule says that if we imagine a man, so here you can see a man, and he is swimming in the direction of the current. The person is swimming in the direction of the current, and the direction of the current is such that the current is entering from his feet towards his face. So the person is swimming in this direction such that the current is entering from his feet and leaving at his head, right? This is the direction of a person who is swimming, right? Then the north pole of the magnetic needle, so here you can see a needle is placed, yes beta, the dotted position. So the north pole of the magnetic needle, it will get deflected towards his left hand. So if the person is swimming over here, his left hand is this side. So the north pole, this is the north pole of the magnet, and this is the south pole of the magnet. So the north pole will get deflected towards his left hand. So you can see this is the deflection of the north pole. So with the help of Ampere's swimming rule, we can predict the direction of deflection of magnetic needle in the Oersted's experiment. There is one shortcut to remember this, and that shortcut is snow. That shortcut is snow. In snow, we are having the word S-N-O-W, right? What do they stand for? S stands for south, N stands for north, O stands for over, and W stands for west. Now let us understand the meaning of this. Snow means, it means that the current is going from south to north. If the current is going from south direction to north direction in a wire, and the wire is over the magnetic needle, आपकी जो वायर है वो मैग्नेटिक नीडल के ऊपर रखी है आपने, तो जो आपका नॉर्थ पोल ऑफ द मैग्नेट है that will get deflected towards the west. This is a shortcut, but I think Ampere swimming rule is best to remember that, right children? So this is your Ampere swimming rule. Let's move further. Now here we are going to study about what is magnetic field, and then we will see that how much force is exerted by the magnetic field on a charge, right? So let's start with magnetic field. So magnetic field, this we have done in class 10th also, that magnetic field is the space, it is the area around the current carrying conductor. So suppose this is your wire in which the current is flowing. So the area around this in which the magnetic effect is felt, in which the magnetic force is felt, जहाँ पे कुछ attraction या repulsion का force feel हो रहा है, that area, that space around the wire is known as the magnetic field, right? So magnetic field is the space around the conductor in which current is flowing, in which the magnetic effect can be felt. Magnetic effect can be magnetic force of attraction or it can be the force of repulsion. उस एरिया को हम बोलेंगे बेटा magnetic field. Now magnetic field is a vector quantity and it is denoted by B, capital B. So capital B is the symbol for magnetic field, right children? Now we are having a very cute little positive charge plus Q. Now this plus Q charge is moving in an external magnetic field B. ये external magnetic field में चल रहा है, right? Very cute one, little one, alone he is moving. The charge, positive charge plus Q. Here we are going to calculate how much magnetic force will be exerted on this positive plus charge. अगर ये external magnetic field B में चल रहा है तो इसके ऊपर magnetic field कितना force लगाएगी, right, on the cute little positive charge. So let's see. Here children, we are having the plus Q charge and the plus Q charge is moving in an external magnetic field B with velocity V, and let the angle between the velocity V and magnetic field B theta. V and B के बीच का angle is theta, right? Now children, the plus Q charge as it is moving, it is going to experience some magnetic force. Now that magnetic force, it depends upon a number of parameters. Firstly, it depends upon the magnitude of the force. कि आपने जो force enter करवाया है external magnetic field में, what is its magnitude? More is magnitude, more will be the force. How children? Because we know when the charge is moving, it produces current. Moving charge produces current. अगर ज्यादा charge है तो current कैसा होगा? ज्यादा. More charge, more is the current, and we know that if the current is more, then the magnetic field will also be more, because in class 10th also we have done that magnetic field is directly proportional to the magnitude of the current. If we increase the magnitude of the current, then the magnetic field will also increase. So इसीलिए it depends upon the magnitude of the charge. The moving charge, more is the charge moving, more is the current produced, and more is the current produced, more will be the magnetic field, and in more magnetic field, more force will be exerted, more magnetic force will be exerted on it, right? So the first parameter on which the magnetic force depends is on the magnitude of the charge, right? Second thing, it depends upon the velocity component which is perpendicular to the direction of field. Let us try to understand this. Now this is velocity, right beta? Now we are going to split it into two components. One is V cos theta, that is along y axis, V sin theta, that is along x-axis, right? Now children, if you see V cos theta, that is along the direction of the external magnetic field. External magnetic field की direction में है. Now, because of V cos theta, the positive charge plus Q, it produces its own magnetic field, and the magnetic field that is produced in such a way that it is not affected by the external magnetic field. Plus Q charge, when it is moving with the velocity v cos theta, it produces its own magnetic field, which is produced in such a way that it is not affected by the external magnetic field. So it will move as it is. No magnetic field, no magnetic force is exerted due to the V cos theta component, right? But the V sin theta component, which is perpendicular to the external magnetic field B, external magnetic field B को ये perpendicular component है. This is the component which is going to produce the magnetic field in the moving Q charge, which will be interacting with the external magnetic field. ये plus Q charge जब move करेगा तो इसकी खुद की magnetic field होगी, and उसकी जो खुद की magnetic field होगी, that will interact with the external magnetic field, and when it interacts, magnetic force is produced. So magnetic force is only produced by V sin theta, which is perpendicular to the external magnetic field. No magnetic field is produced by V cos theta, which is in the either in the direction of magnetic field or in the opposite direction of magnetic field, right? So magnetic force is produced by the V sin theta component, that is the perpendicular component. Third factor on which the magnetic force depends is on the external magnetic field. आपकी जो externally आप magnetic field supply कर रहे हो, it depends upon the magnitude of that. More is the magnitude of external magnetic field, more will be the magnetic force acting on this chotu plus Q charge, right? If we combine all these three parameters, we will get F is proportional to QVB sin theta, and in order to remove the proportional sign, a constant will come, and that constant is K, right? And K value comes out to be 1. So we get F equals to QVB sin theta. Now we know this is cross product, so here we can write, instead of sin theta, in vector form we can write it as vector F equals to Q bracket V cross P, right? So let's talk about the direction. We got about the magnitude, that is F equals to Q V cross P. Now the magnetic force F, how we will get its direction? So its direction can be found out by right hand rule. There are other rules also to find out the direction of magnetic force, right children? You can use your Fleming's left hand rule, you can use your right hand palm rule, right? So according to this rule, what you're going to do is, here the direction of magnetic force is in the direction perpendicular to V and, okay, so this is your direction of magnetic field, and if you are going to have here the positive charge, what you're going to do is, you are going to curl your right hand fingers from the first vector and you're going to turn it towards the second vector. So you are going to place your right hand fingers in the direction of V and then curl them in the direction of B, and then the thumb will point out in the direction of magnetic field. Let me explain you the other rule, that is Fleming's left hand rule. By Fleming's left hand rule, if the first two fingers, if the first finger points in the direction of magnetic field and the middle finger points in the direction of current, then the thumb Then the thumb gives you the direction of force. This is your Fleming's left hand rule, by which you can find out the direction of magnetic force. This is also easy. You can use this left hand rule. Use kare first finger magnetic field, middle finger or second finger current. Then the thumb gives you the direction of magnetic force on that particular charge. Right. Now, magnetic field B, its SI unit is either you can write Tesla or it is Weber per meter square. Now let's move to the motion of charge particle in magnetic field. We saw that if you are having a charge, एक बेचारा छोटू सा charge था plus q, and you have placed it in an external magnetic field. So we know the force that is acting on that charge particle in external magnetic field B is F equals to Q V cross B. This is a force, right? Now, when this force is acting on the charged particle, what would be its motion look like? इसका path क्या होगा? How it is going to move in external magnetic field? Force would be this much. Okay, fine. But what would be its motion? So let's see the motion of a moving charge in magnetic field. Now, here we are having few cases. So this is the force formula QVB sine theta. Case number 1, when the theta is 0 or 180 degree, means the angle theta is 0 or 180. We know that the theta is the angle between B and V. B is external magnetic field and V is the direction of velocity of your charge, right? If the angle between them is either 0 or 180, means if the charge is moving in the direction of external magnetic field or the charge is moving in opposite direction to external magnetic field, then the theta will be 0 or 180. Let's put sine 0 is 0 and sine 180 is also 0. So children, when the charge is moving either in the direction of magnetic field or in the opposite direction to magnetic field, then the magnetic force is 0. No magnetic force. कोई force नहीं लगेगा because of the magnetic field, right? And कोई force नहीं लगेगा तो the charge is going to move as it is moving. So the charge continues to move with the same velocity in the same straight direction. So the path of the particle would be linear. That is, it would be a straight line path when the angle between the external magnetic field B and velocity V is 0 or 180. Right. Now let's see the second case when the angle between them is 90 degree. Angle between the magnetic field B and velocity vector V is 90 degree. So we know the formula F equals to QVB sine theta. Theta is 90 and sine 90 is 1. So now the force is acting. The magnetic force is there. Right? So अब magnetic force उसको अपने रास्ते पे नहीं जाने देगा. The magnetic force उसको अब अपने according उसको move करवाएगा. Right? So the magnetic force that is acting is QVB, right? This force, the direction is 90 degree. So this force acts always perpendicular to the direction of motion. So at each and every point in the direction perpendicular to it, the magnetic force acts. And perpendicular to the direction of motion means the charge plus q is going to move in a circular path. अगर किसी की डायरेक्शन के मोशन के डायरेक्शन परपेंडिकुलर डायरेक्शन में अगर फोर्स एक्ट करता है then the particle is going to move on a circular path as we have done in class 9th centripetal force. We are done na? Take a thread, tie a stone and rotate it, whirl it. So what happens at each and every point At each and every point of direction of motion, the centripetal force acts at 90 degree, and so the particle is moving in circular path. So when the angle between the external magnetic field B and velocity vector V is 90 degree, at that time the charge is going to move in a circular path. So this is your case number 2. At 90 degree, the charge is going to move in a circular path. So the magnetic force Fb will be equal to centripetal force, because we know when a particle is moving in circular path, moon, it revolves, it is moving on a circular path around the earth, right? Why? Because of centripetal force. So यहाँ पे भी the charge is moving in a circular path. So it means the magnetic force is doing the work of centripetal force. Means magnetic force and centripetal force are equal. So magnetic force is Fb equals to Fc, that is centripetal force. So magnetic force QVB, centripetal force we know mv square by r. So if we make r subject of formula, r equals to mv upon qb, because beta vv will get cancelled and you can make r as subject of formula, where r is the radius of the circular path. The circular path which the charge is going to travel would be of radius r. Okay, beta? Chalo. Now from this equation we know for circular motion we know velocity equals to distance upon time. Now circular path distance is circumference of circle. Circumference कितना होता है 2 pi r upon t. So if we make t subject of formula, then we'll get t equals to 2 pi r upon v. T equals to 2 pi r upon v. Okay, beta, this is clear. Okay, now what we are going to do, r value over here we can see here r is there, na? This r value we can put it over here. So on putting the value of r over here, v will get cancelled and your time period formula will be 2 pi m upon qb. Time period of revolution is time taken to complete one revolution. एक circle पूरा complete करने के लिए the time taken by the charge is capital T, which is equals to 2 pi m upon qb. And note here beta, the time period does not depend upon velocity. कितनी velocity के साथ आपका charge initially move कर रहा था उस पे नहीं depend कर रहा है ना बेटा? It depends upon the magnetic field B, external magnetic field B. Right, beta? And from here, you can find out the frequency. We know frequency equals to 1 upon time period t. So if you do the reciprocal of this t, you will get qb upon 2 pi m. So this is frequency is your cyclotron frequency. This frequency is your cyclotron frequency. And here you can see frequency does not depend upon velocity, neither it depends upon the radius of the circular path. Okay, and last part for today, I think we'll be able to complete this. The last part is the third case. Now third case is, case 1 was for theta equals to 0 or 180. The particle was unaffected and the particle moved in the linear motion. Case 2 was when the angle between the external magnetic field B and velocity was 90 degree. We saw that the magnetic force was acting at 90 degree to the direction of motion. So 90 degree at each and every point means it was moving in a circular path. Now, if the angle is neither 0, neither the angle is 90, neither the angle is 180, it is something intermediate, right? So for that, this is your case number 3. So when you are having the velocity v and the angle is theta, the angle between the velocity vector and magnetic field vector is theta. So we will resolve the velocity into two components. Along x-axis is vx and along y-axis is vy. So along x-axis is v cos theta and along y-axis is v sin theta. Now Vx is in the direction of magnetic field. ये देखो बेटा, Vx का direction ये है, and the direction of magnetic field is also the same. So we have already done that when velocity and magnetic field are in the same direction or in opposite direction, then the magnetic force is zero, right? So due to Vx, the magnetic force Vb is zero. Okay. Now let's talk about Vy. Vy, if you see carefully, Vy is making an angle, 90 degree with the magnetic field B, because magnetic field तो आपके along x-axis है ना. So children, that angle will be sine theta. So here your magnetic force due to Vy is QVB sine theta, and we have seen that because of this the charge is going to move in a circular path, and because of this the charge is going to move straight, and because of both of this, because of the combination of straight and circular, finally your charge moves in a helical path. Helical is your spiral. You using your spiral binded books. So in that you have seen that it is helical in shape. So this is the path of the particle when it is making angle other than 0, 90 or 180. Okay, and finally this is your last thing. Here also the magnetic field is equal to centripetal force because it is only keeping the object on a circular path. But here the centripetal force is mv square upon r. So v, which component we will place of v? Because of which component it is moving on a circular path? Because of the y component, that is sine theta. So instead of v, we are going to put v sine theta, right beta? And v sine theta, if you put these values, then you can make r subject of formula. Sine theta will get cancelled, and if you make r subject of formula, it will be mv sine theta upon qb. This is the radius of the helical path. And you know time period. Time period we know, in a circular path we know speed equals to distance upon time. Distance circular path is 2 pi r, circumference of circle, upon time t. So if you make t subject of formula, and instead of v we are going to have v sine theta, because cos theta is not making it move on a circular path, isn't it? So instead of v we are going to put v sine theta only over here. So we will get this equation, and finally your time period t equals to 2 pi m upon qb. Here the sine theta component is making the charge move on a circular path. Cos theta is not making it move on a circular path. Right beta? So this is your new term, that is pitch. Right? So pitch is the linear distance. If you just see in the diagram over here, यहाँ से यहाँ जाने में ये जो linear distance है, that is called pitch, right beta? So that is your pitch. So pitch is what? It is the linear distance traveled by the charge in magnetic field during its period of revolution. Means एक circle खत्म करने पे कितना distance वो x axis में आगे बढ़ा, that is the pitch of the helical path. And your pitch, in pitch we know that linear path is covered because of which component? It is because of v cos theta. So in pitch you are having your beta v cos theta. So this is it children. Tomorrow we will continue further.